Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, let's get started. Hello everyone, good morning. I'm Wolfram Schulte, and it's my pleasure to welcome Jeremy Sieg from the University of Colorado in Boulder. And so I met Jeremy 2 or 3 months ago on a language panel, and I was so struck by his work that I thought, well, we should actually learn more about what he's doing. So the good news is he is an academic who actually influences the C++ standardization committee, which I think is hopefully really helpful in order to get a little bit more sane language. He works a lot on metaprogramming. We are trying to do something similar with C# version 5, and I would like to hear more from you, and I think the audience as well. So welcome to Redmond. Thanks.
Thank you very much, Wolfram. Maybe to give a little bit more background, I've been involved with building generic libraries, things like the Boost graph library, and then that led into trying to improve the support for generic programming in C++. So I was one of the architects behind the new concepts feature that will be going into the next version of C++. And that was the focus of my thesis. But what I'll be talking about today is what I think about as the second part of the language support you need to do really great libraries, software libraries. The stuff with concepts that's going in will very much help with modularity, but it doesn't provide it doesn't have a nice story to tell in terms of the metaprogramming and doing compile time computations. So this talk is about the kind of the research that we've been doing in that direction. The title, Type-Safe Reflective Metaprogramming, it's not a claim about what we've achieved, it's a goal. And I'll be talking about some of the explorations that we've been doing in that direction and some of the problems that we're exploring. So metaprogramming is really hitting the mainstream. Okay, people are writing lots of programs that create and manipulate other programs. It's just the usual automation. Why do something by hand over and over again if you can automate it? And so there's been a bunch of books on the subject, and uses in real applications, whether that be the Boost libraries. That's what the left two book, or basically the three left books here are mostly about C++ and how like the Boost libraries use metaprogramming. But then you're also going back as far as Lisp, but now looking at Ruby. These dynamic languages have for a long time done lots of metaprogramming and benefited from that. So it's really hitting the mainstream. And that really motivates us as language researchers to try to provide excellent support for those capabilities. On the research side, there's certainly lots of going on to support metaprogramming, and Scheme, for example, has a really interesting macro system that does the right thing when it comes to variable binding. Okay, unlike earlier like Lisp macros and things like that. There's work like Template Haskell, MetaOCaml. I did a postdoc with Walid Taha a couple years back and learned a lot about his work on MetaOCaml, and that's a pretty big influence on some of the stuff we'll be talking about today. Here at Microsoft Research, I know that there was work by Manuel on Spec Sharp with compile time reflection. So that's closely related to some of the stuff I'll be talking about. And then for those of you from OGI, the Omega, Tim Sheard, is also sort of in this family of languages. So C++ has been been a really interesting sort of experiment, whether it be a sandbox. You can think of a sandbox in which programmers can play around with these features and see what they're useful for. You can also look at it as a petri dish, where all kinds of strange things grow and, and can be discovered. This is actually my daughter here on the on the right. So there's all kinds of interesting techniques that people have come up with. I think one of the kind of overarching ideas that's really paid off a lot is this notion of domain-specific embedded languages. And really, this is just an outgrowth of the notion of a library. You want to make your library smarter. You want to make the syntax more interesting. You want to do optimizations that are specific to that domain, whether that be like linear algebra or regular expression, and so on. And so then techniques like, for example, expression templates is an approach to optimizing these domain-specific languages. And what's really interesting about sort of this style of metaprogramming is that you can do it with a standard language. C++ out of the box supports all of this. You don't have to change the compiler. You don't have to go under the hood and change the language to do this kind of metaprogramming. It's just layers on top. One of the other key sort of facilitators in being able to do this is that you can essentially encode compile time computations in C++. And as the library writer, you can sort of take control of what's happening and choreograph how you want the execution to happen. That's taken care of at compile time, and then what happens at runtime is really fast and efficient. One of the other really interesting parts is the domain-specific static checking. We'll talk about an example of that in a few minutes. But you can basically hijack the type system to do extra checking. For example, let's say you want to check the units of numeric quantities. You can encode that with templates and then force the compiler to check those things. And so this is a great way of making your library even safer to use because you can enforce it at that point. One of the last things I want to mention is generative components. The idea there is that oftentimes as a library writer, you feel like you have to make certain decisions and fix them in stone and then distribute your library. And oftentimes these decisions are hard to make and may not be the right decision for some users. And with generative programming, the idea is that you can allow some of these choices to be made by your user. You can give them sort of dial up what kind of component they really want, push the button, the metaprogram churns and spits out the exact component that's right for their use. And so that's a nice tool to have as a library author. So C++ has been a great sandbox. It's allowed us to make libraries more flexible. They've been more efficient, and we can also make them safer with that static checking. But there's a huge host of really serious problems, okay? And it's basically become notorious for some of these problems. When you start doing sophisticated metaprogramming, the compile times get completely out of control. The metaprograms themselves are difficult to read and debug. There's these funny angle brackets everywhere. And it's almost like learning a whole new language to be able to read and write these metaprograms. And from a modularity point of view, one of the biggest problems is that the metaprograms themselves are not type checked. It's almost like you're writing in a dynamically typed language like Lisp, okay? And the output of your metaprogram will generate C code, and that code will get type checked. But that's sort of late to find out about a problem in your metaprogram. And we'd like to find out about bugs in our metaprograms earlier. And then there's a host of funny limitations. So there's all kinds of interesting things you can do in terms of reflecting over types and classes in C++. And I'll never say you can't do something in C++ because we're always learning new ways to trick it into doing things. That being said, there's certain kinds of things like querying class members that there's no sort of straightforward way to do that. And so in a language that's actually designed for metaprogramming, it's be much nicer to add in and sort of flesh out these kind of capabilities. So let's take a closer look at this Petri dish. We're going to be looking at, kind of briefly looking at a bunch of different examples to kind of see what are people doing with these metaprograms. And in order to read those, you'll need to understand template specialization. This feature is sort of the workhorse of metaprogramming in C++, for better or for worse. So what we have here is a template. We'll call it the primary template to distinguish it from these other templates down here. Here we have a static, one static data member, I, and it's being set to 0. Here we have a specialization of that x for the situation where the first parameter is an integer. Okay. And then here we have another specialization for when the second parameter is an integer. And then let's sort of see how resolution works for templates. And basically the notion is that when you have a reference to a template, it resolves to the most specific fit in a pattern matching viewpoint. So this guy does not match either of the specializations, so it resolves to the primary template. The second guy resolves to this template. The third guy resolves to that template. And then last but not least, we have an ambiguous case where you have no most specific match and you get an error message from the compiler. Okay. When we start looking at these metaprograms, we're actually, you want to think about these classes almost as if they were functions. And you want to think about instantiation a lot like function application. Okay, that's kind of it helps to have that mental model when you're looking at some of these metaprograms. Okay. Any questions at that point? I don't want to jump through that too fast, or we won't be able to talk about the rest of the slides. But.
Because when you say most specific, you mean that all the choices have to be ordered by getting more and more specific, and then you pick sort of the minimum, or?
It's not that a priori the choices have to be ordered. So this can form a partial order, but when you then sort of look at a particular instantiation, for that guy there has to be a most specific one. Yeah.
Just for clarification, what's the determination for most specific?
So what it means is that there has to be, well, basically, so what's the ordering amongst these guys? It's basically one of these guys is more specific than the other guy. If you can take this guy and instantiate some of his parameters to get that guy. Okay? So there's no ordering relationship between these two guys, right? So, or, yeah. Yeah, it's actually the same kind of ordering relationship between type schemes and ML. Okay, any other questions on that? So here's a simple example of doing a computation at compile time in C++. It's the good old greatest common divisor function. It's probably, here I'm comparing it to a normal function written out in Haskell that computes the GCD. Notice that it's doing pattern matching on its parameters and then choosing, one of these cases or to recur in that last case. And so looking up here, we've got a primary template that handles the sort of the situation for arbitrary x and y. And this enum is just one way of sort of writing a compile time constant. The thing on the right-hand side has to evaluate it at compile time. And then here we have two specializations that handle like the base cases of this function. And this is really sort of an error case here. Okay. And so, for example, in C++, you could do a call to this GCD function and use the result as the size of an array or something like that, something where you need to know at compile time. You can also use this kind of thing just to speed up some kind of computations. You don't want the computation happening at runtime. You want to hoist it into the compile time. So go ahead.
GCD is actually then unfolded and compiled.
That's right.
And then reduced.
So let's say here. Let me. I could do something like int array. GCD of 132 value. And so this would get evaluated at compile time during compilation, and then at the end of the day there'd just be a number here. Or like, let's say this was involved in an arithmetic thing, it would just be like an immediate in your machine instruction, right? And sort of one thing to point out here is that really what the template specialization is giving you this pattern matching facility. Okay, so you've got this pure functional language with pattern matching is kind of what you're dealing with in this template system. Here's another little example. This time what we're doing is partial evaluation. So we've got a function like power that takes two inputs. We are going to set it up so that if we know one of the inputs, the m, at compile time, we can sort of do some of the work and then leave the rest of the work for runtime. So what will happen with that pow n of 5 at the bottom is that the actual code that gets generated by the compiler, assuming that it does all the right inlining, is that it'll have n times n times n times n times 1. Did I get my number of n's right? One more. Okay. Thank you.
What's kind of funny is it would kind of generate 5 pow n functions, right?
That's right. It would generate 5 functions specialized for 5, 4, 3, 2, 1. The 5, 4, 3, 2, 1 are all from the primary template, and then the final base case would be that guy.
But it wouldn't interact with overloading. It would all be pow n that take int.
That's right. Right.
Right.
And that's why I said that the caveat about inlining is that so you've got all these functions, and then you're hoping that the compiler will inline it down to this. And this is a fairly easy job for the compiler to do. These are all direct calls. There's no virtual function funny business going on. So it's easy to inline, but relying on a compiler to do something is always a slightly dangerous thing depending on how much of a control freak you are. Okay. Here's a snippet of the expression template technique. I've simplified it a little bit, so for ease of understanding. So depending on how you do it, this may or may not work exactly as posted, but it should get the basic idea. So at the top there, we've got what a user of a linear algebra library would like to write. They can declare their vectors, and then they can do vector operations. And if you implemented this in a naive fashion, every operator would do its computation. It would add a and b, create a new temporary vector, and then it would then divide that element-wise, for example, with the result of c minus d. Whereas, if you're thinking, if I'm going to write this by hand and I'm a knowledgeable programmer, I would just write one loop. Do this all in one big loop. And in doing that, you would have reduced the memory traffic significantly, okay? Which, of course, is sort of the important thing on modern architectures. So what this expression template trick does, it says, okay, instead of having your operator plus actually do the computation, it's going to be sort of lazy about it. It's just going to return a tree that represents the computation that needs to happen. Okay, and that's what this add expression is doing. This should have been expression or something. Yeah, that's bogus. Cut and paste error. So this encodes the tree, and then when you finally get to the assignment over here, at that point, you can use your, all your metaprogramming tricks to decide how to implement that. Here's a particularly simple way of doing it. You have your loop, and then you basically just call this operator bracket to say, give me the ith element of this expression. And that will then, if it's an add expression, it'll be doing this addition on two elements. You can imagine what the division and subtraction expressions would look like as well. So this is a fairly old trick now. It goes back to the 90s. Todd Veldhuizen was one of the main guys behind developing this trick. But it's a really nice way to have your cake and eat it too. You can write your nice syntax, and then the library can sort of decide how it wants to optimize the computation. Okay, the next example, this is the unit checking example that I promised to talk about. The idea here is that you can create your quantity class as a wrapper around the actual value, which would be typically like a double or something like that. And then you could encode in the parameters here the dimensions. Okay. So for example, mass would look like that. Velocity is length over time. Okay. So that's how you read that. And then, for example, in our operator plus, we can ensure that the dimensions match up appropriately by carefully choosing the parameters or the arguments that we supply to this quantity class. And the fact that we've given it the same length, the same mass, and the same time parameter in these places is saying that they must be equal in order for this plus operator to match. If they're not equal, this operator plus won't apply. There's probably no other operator out there that could apply, and you'd get an error message, right? And you'd prevent your rocket from having a bug and crashing horribly, right? And so here's an example where I'm trying to add a mass to a velocity, and it dies. There's been a fair amount of work on adding this kind of unit checking directly into programming languages. And kind of coming from the C++ point of view, that seems sort of funny. We'd much rather add sort of generic support for doing this kind of metaprogramming and index this is called sort of parameterizing or indexing a type by values. And with that generic support, then we can then encode all kinds of stuff, this and much more. Okay. Okay, I think this is the last piece of C++ code, one of the few last ones that we'll look at. So the notion of this notion of generative programming is mostly due to Sarnecki and Eisenecker. And kind of the idea here is that oftentimes a particular data structure like a list, there's no one best language or library design for that data structure. This is one of my favorite little examples. Should a singly linked list include a counter that keeps track of its length or not? Seems like an easy decision, right? You say, yes, of course. You want to know its size in constant time. You don't want to have to traverse the list to figure it out. But guess what? If you do that, you can no longer do sort of arbitrary splicing operations of singly linked lists in constant time. Okay? If you're splicing out of the middle of some list, you have to go and count the length of that region. Okay? So if what you're doing with lists is lots of splicing, the last thing you want is a length counter, right? So you want to let your user choose. Okay? So that's the notion behind this list generator metaprogram, is that it has all these parameters to it, including like a flag to say whether or not you really want a counter. And then when you instantiate one of these list generators, for example, without a counter, the type that pops out is going to be, the one that you wanted for your application. Okay.
That means that inside your class definition, there must be lots of if statements, like if I have a counter, then do this, otherwise.
That's right.
Okay. That makes it harder to make sure that your generative, list is actually correct, right?
That's right.
You may do things in your if statements.
That's right.
Don't mean certain other. You have to check all your possible variations.
Yeah. Yep. So I won't have a chance to talk about this. I don't have a slide for this, and this is more sort of future work that we're looking at. But one of the approaches that we want to take to this is to use the constraints and concepts feature together with existentials to describe the return type of this generator. So we want to be able to say that this generator, whatever it returns, is something that sort of conforms to a list interface. So whatever, you've got all these if statements inside, but every branch is supposed to return something that implements list. Okay? But this kind of existential that I'm talking about is something that only lives at compile time, and it just makes it possible to do your compile time. It makes it possible to type check your metaprogram before your metaprogram executes. We can already type check the results of the metaprogram, but we want to move it earlier. But this is sort of future work that we haven't got to yet. We're sort of still taking sort of baby steps to get there. But that's one of the main challenges ahead of us, is to deal with that.
This looks nice. To me, it seems like forget about, pre-processing, use this instead.
Mm-hmm.
Now, one thing I'm wondering is how much switching can you do? Like, can you, for example, provide certain methods only if, a certain argument is wrong or not?
That's right. Yes.
Can you do all that?
Yeah. And getting back to the template specializations, there's no constraints in the C++ language on what one specialization has or doesn't have in terms of methods. And so basically you could imagine this guy internally sort of dispatching off to different specializations. Yeah.
But you have to write separate specializations. You can't have an if statement that says something like...
Well, you can have ifs too.
So the ifs?
Yes. Yeah.
Substitution failure, not an error.
Well, that with an enable if. But you're talking about something simpler, which is just sort of a normal, like if true, give me this type. If false, give me this other type. I had the privilege of showing Bjarne Strustrup that was possible in his language. The idea comes from, I think one of the earliest ones was Czarnecki, I think. When he was doing this work on these generative libraries, he showed how to do an if statement. And it's actually a simple class called if with two specializations, one for the true case and one for the false case.
Excuse me, for so many configurable parameters here, so how will you make sure this is right? How will you do testing or dev testing for this complete class?
That's very, very good question, and that's really at the heart of this problem. Because in C++, right now, there's no type checker that analyzes statically your generator and says whether it's correct or not. So you just have to, just like in a dynamically typed language, you have to have a really good test suite, right? And you have to try it with all these variations, which is arguably difficult to do.
Also, just a reminder for any questions from people reviewing.
Oh, okay.
Yeah, but I was going to also comment that one way that I've been doing unit tests, of course, is you have a source file that you compile that has no code in it. Whether or not it can be parsed correctly by the compiler proves whether or not your metaprogramming code executed properly.
That's right. Yeah. That's a trick that we use quite a bit. Yeah. Yeah. There's a whole for my Boost graph library. I use these generators for generating graph data structures, and then there's a whole bunch of test files where if they compile, that's success. And the Boost regression testing framework had to have that as one of the kinds of tests that it can run. It's just the compile test. Yep. So now we've seen sort of what's in the petri dish. What are all the different things that people are doing with metaprogramming? And what I've been trying to do is take a step back and kind of see what are the sort of essential properties that are in language features that are enabling these idioms, these techniques. And then can we then sort of provide more straightforward language features that enable these techniques? So obviously, one thing that's going on is that we can do computation at compile time, and that we can very conveniently embed compile time computations in the actual runtime language. In particular, like from a library author standpoint, like the fact that my units library does this static checking is transparent to the user, except for when they get the error messages, which is when they want it, right? But they don't have to know that, oh, I'm sort of triggering a compile time computation at this point. It's just I'm calling a library function. Oh, and by the way, along with the runtime stuff that happens, there's also this compile time stuff that's happening. Okay, the compile time language in C++ is Turing complete. You can really do just about anything you want. There's a lot of research and looking at sort of trying to not be Turing complete and look at sort of decidable subsets and things. Coming from the C++ point of view, and I kind of go back and forth on this myself, but there's always, whenever you do that, there's always this worry that when you're actually writing your app, you're writing your library, you're going to hit a wall and run into something that's not easy to express in some decidable subset. So that's why there's this, kind of this leaning towards, hey, let's just make it highly expressive. This compile time language of C++ is pure functional. It's kind of funny that if you were to try to get a C++ programmer to write something in Haskell, they'd complain day in and day out about trying to write something pure functionally. But a bunch of those same programmers will stay up very late at night hacking away on template metaprograms that also happen to be pure functional. I don't know why that is so sociologically or psychologically, but anyways. We can, in some sense, treat the runtime code as data in our compile time programs. Okay, we can essentially pass functions around, splice them together. It's a little weird how you have to do it. It's basically relying on inlining to make that happen, but you essentially have that capability of splicing things together. And then the other really interesting feature is that you can treat types as data. You can do pattern matching on types. You can you can do a computation that computes a type and then uses that to type the runtime code. In some sense here what we have is the type of this variable is depending on the result of GCD. Okay. So I view that as these sort of as the essential properties that's going on in C++.
What's the difference between code and runtime code and types in there? Because you cannot reflect on runtime code, but you can reflect on types. So there is a big difference.
Yes, actually that's an excellent point. So this has to do with sort of whether you sort of treat code sort of extensionally or intentionally in terms of how you can manipulate it. So this is, C++ takes the extensional point of view. You can't pull apart a piece of code and look at its AST and then manipulate it. So whereas like in Lisp macros, you can. In template Haskell, you can. You can pull it apart and look at the AST. So the C++ setting is actually closer to the family of research languages like MetaML, where you're not allowed to pull the code apart. Okay.
So can you say what scenarios are prohibited by taking the code apart? So what feature would you get in addition?
If you could take code apart? So once you, with the capability of taking the code apart, you basically have the full power that any compiler has to rewrite pieces of code and optimize internally. So you could create a piece of code and then rewrite. In C++, once you've created a piece of code, that's it. You can't then further change it. Okay. Though oftentimes you can get similar kinds of behavior out by, instead of sort of creating the piece of code to begin with, you might create some compile time data structure that's a lot like an AST, like those expression templates, and then manipulate those around and then finally generate your piece of code. So is there a fundamental restriction? I'm not sure.
But you could query the types and then create a class with a function to manipulate it at runtime.
That's right. That's right. Yep.
You couldn't do it all in compile time, but you could create something to do it at runtime. That's right.
Yeah, so I'm not sure if there's sort of a fundamental difference in expressivity, but certainly a lot of things would be easier. Like let's say you wanted to do common sub-expression elimination or something. It'd be sort of really hard to do that. You couldn't do it in a straightforward way with the extensional approach. Yep. And the other trade-off, why do people like the extensional approach? There's more hope of being able to do type checking ahead of time. So for example, with MetaML, I'll be talking a little bit more about this in a few minutes, but because it's extensional, you actually can do the type checking up front. Oh, actually, this is the next slide. Okay, so first I just want to talk about sort of this aspect of treating code as data. And so this is a really old idea. It goes back to Lisp and their notion of S expressions. And they've got this capability of quasi-quote, unquote, and eval. Okay, so for those of you that haven't seen Lisp in a while, what we're doing here is this quote is introducing a chunk of data that happens to be also a piece of code. Okay, and so this piece of code will add 1 to this thing over here. The comma here, the unquote, says, okay, I'm not creating data anymore. I want to go ahead and execute this now. Okay, and then splice it in to the piece of data that I'm generating. So the result of this will be a piece of code that has that when this is run will add 1 plus 3, which you can do with eval, to get 4. Okay. So this is sort of the 3 main sort of things you need to treat code as data is quasi-quote, unquote, and eval. In C++, it doesn't you don't explicitly have these constructs, but you can basically template specialization and calling function templates and things can sort of mimic the same kind of splicing behavior. Okay, so in MetaML, so here's a good image to keep in your head, which is when you're doing this metaprogramming, there's 2 stages. There's the compile time, which is also the time when the meta evaluation happens, and then there's the runtime when the actual program runs. Okay, and in C++, this is where the type checking happens. Okay, so your template metaprogram runs, after that, you just have sort of a normal, sort of almost C-like program, which is then type checked. Okay. Now, what's really cool about MetaML is that MetaML, it'll type check the metaprogram here at the beginning of time. And that one type check guarantees that not only will it run, the metaprogram run without error, without type errors, but also it guarantees that the actual runtime code will go without error as well. Okay, so this is a pretty powerful guarantee. And one of the main ideas behind that is that when we create a piece of, a quasi-quoted piece of code, it gets assigned a type, a code type, which is this bracket here is sort of saying this is a code, and then the T is then the type of the thing inside. Okay, so what's happening is during type checking of the metaprogram, it's also sort of reasoning about these code fragments in the runtime program, because that's what's inside, that's what the T is, that's the type of the runtime code. Okay. So if you're trying to write a little type checker for this, I'm simplifying a little bit from MetaML. MetaML is a multi-stage language. You don't just have level 0 and level 1. You can have an infinite number of stages. But typically, in what we do, we only need compile time and runtime. So this is what your type checker function would look like for dealing with your quasi-quote and your unquote. So let's say you're trying to type check your metaprogram. What you're looking at is a quasi-quoted expression. Well, then you go ahead and recursively call the type checker, not the meta type checker, but just the type checker on E, get back the type for that, and then what you return as the type of this quasi-quoted thing is something of type, code of T. And then down here, when you're type checking the runtime chunks of code, you're going along and you might hit an unquote, okay? And then what happens there is, now I need to escape back to the type checker for the metaprogram, get some type out, and then you're like, oh, well, we're about to splice this in. So this type T better be actually be a code type. And then we now know that T prime is the type for the unquoted thing. And that better jive with the context of where it's being spliced in into the piece of code. So that's sort of fairly straightforward. Once you decide to be able to represent the runtime code with a type like that, then this kind of falls out and gives a nice way to do it. Now there's a whole bunch of complications in type checking MetaML that have to do with being able to do an eval. You can you can generate code that has an eval in it, okay, and then and sort of recursively on down. So that's really the hard part. And there's all this notions of, do you allow pieces of open code or closed code when you're calling eval? Luckily, in the work that we're doing, we don't need eval. We don't have it in C++, and there's lots of things we can do, and we're sort of satisfied with that amount of expressivity. That's not to say that there aren't really cool things you can do with eval, but that's just sort of beyond the scope of what we want. Okay, so that kind of concludes the kind of looking at code as data. And really, I view these constructs as sort of capturing the essence of what goes on with code as data. So kind of going forward, if we were to do sort of a new version of C++ someday with explicit support for metaprogramming, I would want to see essentially a quasi-quote, unquote in the language. It wouldn't have that syntax, of course. We'd probably come up with much more verbose syntax for C++, but that's the main idea. So we also have this notion of types as data in C++. And this is also a rather old idea. A French mathematician named Girard came up with this thing called System F, which allows you to compute over types. And but what's sort of interesting is that what we really need to do is we want to combine that with our quasi-quoting facility and and actually create a unified meta language that can both compute with code and compute with types. And that's actually, from what I can tell, that's sort of a novel idea of trying to compose those into the same language. Some of the work on like Omega and things like that, they can compute over types and they can compute over code, but these are actually slightly different languages. They keep these things separated. Okay? Whereas what we're looking at, kind of inspired from C++, is actually composing these into the same meta language. But doing this composition really sort of stresses out the notion of being able to achieve static type safety. Okay? So here's a simple little program sort of in sort of this kernel calculus. Okay, so we can, starting in here, we've got a piece of quoted code. Okay, so this is some runtime code. But note that I'm splicing in a type for x. Okay, and some compile time computation, meta computation, is going to determine what that t is going to be. And that'll happen, and this lambda out here, this function is a compile time function. I could, at compile time, I could have an if expression here. It's going to evaluate, x will evaluate to int, and then f of x will plug int in here, and then finally splice the int in there. Okay, but if we want the same kind of MetaML guarantee where you type check before meta evaluation, well, how can you know what the type of this piece of code is if you haven't evaluated t yet, right? So that's this really hard problem, and I'm sorry to say I don't exactly have the ultimate solution to that yet. And in some sense, there may not really be a solution, but it's still good to have these kind of goals, to sort of hard goals to drive you forward. I know we're jumping into sort of lambda notation.
This is a very, so if you allow, if you want to be both true and complete, then you're always going to get this, right?
Yeah.
Where you can't determine what type's really coming out.
That's right.
So you will, either you're going to reject it, or you'll never be able to really type check it, right?
Yeah. So we're, a lot of the research, at least especially the early research we're doing, is looking at, are there points in between these two extremes of rejecting it outright or just waiting to type check? Is there things in between that we can do? So let's go ahead and.
In MetaML, they carefully kind of reject these kinds.
That's right. They would never. MetaML would never let you do this.
That's right.
Right. You can't have the types of your code depending on meta evaluation.
So have you found a convincing example where you want this? Maybe in the first library.
Yeah, actually, this kind of stuff is all over the place.
Oops, okay.
like those expression templates. A lot of times, like the return value for operator plus. Like in that example, we just had it was an add expression, but oftentimes the return type will actually be some type that's computed by a meta function.
Traits.
Yeah. Yep. So this stuff is all over the place.
You also get it when you keep your units or dimensions or something, vectors or matrices. There's this.
That's right.
If you want to keep it as a type, then you also get the same kind of problem.
That's right. Yeah. The unit, like in not addition, but let's say you're doing multiplication, then the units in your output will be like some error. You'll be adding, the units from the input to get that. Yeah. So for the rest of the talk, we're going to be playing in this little core language. It's pretty much based on the lambda calculus. So the E's, that's the category of sort of your normal runtime expressions. Okay, and it's basically the lambda calculus, but now we have the types for a variable can depend on some meta computation. And you can also splice in meta computations. Okay, and then here's the meta language, which again is pretty much the lambda calculus. This time our constants include things like type constructors. So we can, for example, this could be you could say int here, and then that could show up as, down here is the type of X. Or you could have some function that you apply that finally spits out int at the end, or something like that. You have normal application, and then you also have this quote which says, okay, I'm building a piece of code, and then inside of that you have the e's. Okay. Now, the type annotations for the meta lambdas are more restrictive. These are just this set of types, int, code, bool. Depending on how you want to do the type checking, we've got some options. I already talked about sort of the MetaML approach of saying, okay, you have a piece of code, and then inside the piece of code you have the type of that code, which in this case is actually, because of this dependency here, the way we categorize types of code is actually with meta expressions that evaluate to types. An alternative, sort of simpler approach is to just use sort of a one type for all pieces of code. And you could just call that code. And this would essentially treat code as almost like a dynamically typed thing. Okay? We'll talk a little bit more about that in a second. And then also, when we're trying to give a type to a lambda, sort of a straightforward approach would be to use sort of your typical function arrow. But we'll also talk in a few minutes about using a dependently typed product to type that. And this will actually turn out to be a really natural way of looking at the types for these things. And one I should explain some caveats here. This core language is really meant as a design tool to help think about designs for the actual language feature that would go into C++ or into other languages. It itself is not for direct use. There's all kinds of syntactic sugar that you'd want to add on top of this. In particular, you'd want some kind of macro facility so that you can hide when you're escaping into the meta language. Here, like every time the user of some meta library wants to cause a compile time computation, they have to do an explicit splice. So you want to hide that kind of stuff in a real language. So in general, what we'd end up doing is would have the real surface language, and then you could imagine compiling down to something that looks more like this under the hood. So I want to talk about basically 4 different approaches and directions that we're looking at in terms of how to type check the metaprograms. Okay, type checking even before meta evaluation to try to get towards that ideal of the way MetaML does it, but with a lot more expressivity is what we're hoping. So we're going to look at treating code as a dynamic thing. We're also going to look at something called incremental type checking, which is an idea we had this past fall. We'll also look at the relationship with dependent types. And then the last thing would be we're going to talk about using GADTs to talk about the type safety. Okay, so my good friend Ron Garcia, he's another participant in this NSF project. Just finished his PhD thesis, and in that thesis, he studied just using plain old code as the type of a quasi-quoted thing. And this, as it is, this is a fairly faithful representation of what C++ does. Okay, so though it's one improvement. So with this approach, you don't know whether the code that you're generating from your metaprogram type checks until metaprogramming is completely done. Okay, so that's sort of the same as C++. The one thing that's better about or not the one thing, but one of the things that's better about this approach that Ron was using is that you're still type checking the metaprogram. So if you're doing really stupid things in your metaprogram, that'll get caught with respect to things other than code. Let's say you're passing an integer to something expecting a string in your metaprogram. It'll still catch those errors. It doesn't catch any errors regarding splicing code together. Okay. And this is highly flexible. You get sort of the usual advantages that you get with dynamic typing, but you also get the typical disadvantages. So this past fall, we started looking at something we call incremental type checking. And the idea here is that we're going to, in some sense, incrementally or continually type check all the pieces of all the code fragments that are flying around in your metaprogram during meta evaluation. Okay? And as soon as you splice something together that doesn't make sense, you would halt the meta evaluation right at that point and give an error message. Okay? So this isn't quite as nice as finding out here that there's a problem, but it's much better than finding out down here. And the reason is that it makes debugging a lot easier, because typically you'll be able to much more easily track the cause of the error in your metaprogram by looking at by seeing it get halted here, whereas back here you're staring at the final result of your metaprogram, and then you have to sort of reason your way back through the evaluation to get to the error. So we see this as sort of an interesting middle point.
So does it also mean that you would start type checking as far as you can when you hit these if statements, like if true then int else bool, you would kind of wait there until it's actually used, or
yeah,
how you actually use it, right?
I'll tell you a little bit about how this works. I apologize. This is start to get a little bit more deeper into type system-y kinds of stuff in terms of how we actually implement this. We'll just have a few slides on this. So right now we're kind of thinking in the setting of a Hindley-Milner type system, a lot like an ML style language. And from a type system point of view, imagine the metaprogram is computing along, and what we're actually going to do is run the type checker at every step. That's a mental model. It's not an actual implementation, but that's a mental model, is that you run the type checker at every step. And so you can, the type checker specification is one of these type systems. And so if you have one of these lambdas, this is a code lambda, if the type is not yet evaluated, this M is some arbitrarily large meta computation, then we do what you would normally do in ML, which is you would infer a type. Okay? And as long as you can infer a type that makes sense for its body, that's okay, and you can keep chunking along. If at some point that meta computation finally resolves down to an actual type, at that point you now require essentially that the inferred type and the specified type are the same thing. Okay? Any questions about that? We'll do a quick example too to see kind of what that looks like. So here's a little program again, and at sort of the very first time we type check this, this T here is not yet evaluated, so we're just going to infer a type for it. But because of the body here, it's going to turn out that the type for this function is going to be int, right? Because it can infer that from the +1. So this thing will have type int plus or int arrow int. It's quoted, so that means that the meta language, now the type has brackets around it, and then the type of f will be something that takes in a type and returns a piece of code. Okay. And then down here, we have f applied to x. X is a type. Okay, so that's fine. The result is a piece of code. It gets spliced in, and then we're type checking this piece of code, and we have an int applied, a function that takes an int applied to an int. So that's all legitimate. Okay, so at this very first time we type check, it would say fine, keep going. Okay, so then it would start evaluating to here. It would do another type check here that would pass, and then it would get to this point where it actually spliced in the bool into there, and at this point you'd get a type error. Okay. So that captures the kind of this notion of incremental type checking. One other little example just to see how this interacts with let polymorphism. The type that it infers for one of these unfinished computations could very well not have any constraints on it at all, in which case it would infer that this thing is polymorphic. And then, for example, you could use this meta function with both an integer or a Boolean in different contexts, and that would be fine. Okay. So that type. So I explained the type system and gave you a feel for that, and that sort of specifies, what the type checker should do, but it doesn't give the implementation. The implementation is actually fairly easy. Okay, most ML, or at least some ML implementations like OCaml, for example, use Huey's algorithm for inference, and this is based on a union find data structure for keeping track of which types are equal to each other. And union find lends itself naturally to inference, because as you're going along, you can decide to union two things whenever you want. So the idea is that during meta evaluation, we just have this big union find data structure off to the side, and whenever a result type, like x:t, whenever that result finally comes available, we just do another union on our union find data structure, and it'll either say, "Oops, you tried to union things that aren't compatible," in which case you have an error. Otherwise, it just reconfigures the data structure, and we keep going. By the way, how am I doing on time? Another 10 minutes, or? Oh wait.
Yeah.
Or how much time?
We speak for an hour, so maybe
How?
we
Or
can
how?
ask
Oh, I'm a little over now, aren't I? Oh, okay.
ask the audience and see whether we would probably just wrap up, and people who are interested in the other exploration could stay. And go on.
Great. Yeah, I apologize. I didn't have time to record or to predict how long this would take. So, yeah, but we've hit a good chunk of the material.
Okay. We sometimes try to wrap up and then get to the remaining slides.
Sure. Or actually, there's a fair amount left. Maybe I should just kind of summarize. And then maybe later on, if people want to talk about it, we can do that. One of the things we want to do is relate the C++ metaprogramming in this little core language that we're talking about, relate it to existing research out there, and in particular, this classification called the lambda cube. And this has inspired some further work on thinking about how dependent types can be used in our system. And maybe I'll just leave it at that as an advertisement for that. And then the last approach that we want to look at is actually kind of taking a step back. And in many situations, you can think about a metaprogram as taking as some input, some domain-specific language, and then reducing it down to the base language. And if we want to make sure that this thing is correct, well, we kind of need to do the normal thing of establishing some preconditions that are strong enough to carry through to establish the postconditions. And we'd like to have some automated way of actually proving that this thing, based on these preconditions, establishes the postconditions. And there's this really cool language technology for talking about constraints on AST, abstract syntax-like things called GADTs. And using GADTs or extensions thereof, we can express not just what this AST looks like, but also put constraints, for example, expressing a type system, or all kinds of other constraints. And similarly, we can do that for the base language. And then we can have the type checker of the metaprogram be GADT aware, and actually, if this type checks, it will have proved that we actually generate something that satisfies those postconditions. Okay. And I had some examples about that. This is sort of a diagram of how we sort of envision sort of being able to create language extensions using this approach, where you have your base language with a grammar and a type system. and a compiler. And then you have your language extension with a grammar for your little extension, type system for the little extension, and then macros that say how to expand your new thing into the base language. And then based on all these pieces, you generate the actual parser for the full language, the TypeChecker for the full language. It would generate a GADT. It would go into this macro. This macro would have already been type checked using the GADT aware. So we know that whatever comes out is going to be a well-formed GADT for the base language, which means it's type checked and solid. And then that'll run through the compiler. So this is sort of this overall vision that we have. And this sort of gelled for us just recently. I mean, there's some similar kinds of things going on elsewhere, but we're really excited about this approach to language extension. Okay, as sort of a fun test case, what we hope to do is actually take some language features that would normally sort of be very much core language features and see if we can do them as a language extension. Can we do classes? Like in an object-oriented language, can we do those as a language extension? Can we do type classes a la Haskell as a language extension? And what gives us a little bit of hope that we can actually do this is that people have done it using scheme macros in an untyped setting. And so then the question is, can we do a similar kind of thing using GADTs in a fully typed setting? Okay, so just to wrap up, so metaprogramming is hitting the mainstream. It's helping us improve libraries. But there's still a lot of pain because there's a lot of immature language technology out there, most notably C++. And I've talked about three directions that we're looking at in terms of trying to move towards type-safe reflective metaprogramming. All right.
Yeah, first let's thanks. So maybe we take some questions, and let me also add that Jeremy is here until tomorrow around noon. So if you want to meet him, let me know. And we can set up a schedule. Okay, but maybe more questions.
Okay.
I just want to ask your example of the vectors seem to imply that one of the points of doing this was to make it so that the runtime code was actually quite efficient.
That's right.
Is that generally borne out for this kind of programming, and is the gap between C++ performance and other languages getting small enough where it might be worth not doing this in C++ at all, but just using a language that's maybe more well designed for it?
So kind of what other languages do you have in mind as sort of comparisons? So, well, in terms of performance, the only language that beats C++, I mean, of course, it depends how you write your program, right? But in general, the only one that can beat it is Fortran. And it's for one very small reason, or a big reason, the way you look at it, is aliasing. Fortran has a built-in no alias assumption on parameters that the compiler can take advantage of to do optimizations, and C++ doesn't. It takes a more conservative approach and doesn't have that restriction. So that fundamentally is the only difference that affects what kind of machine code will get generated from a C++ versus a Fortran program. And that sort of has nothing to do with this metaprogramming issue. Now, with getting back to this expression template stuff, obviously you can't do that kind of thing in Fortran. So in Fortran, what you'd end up doing is if you wanted the same kind of performance that you'd get using an expression template, you'd write it out by hand. Okay? And so kind of what's sort of unique about C++ is that you can get Fortran-like performance and be able to use some abstractions and create domain-specific languages. And there's really no other language that lets you get that extreme performance in that setting. I mean, Java, C#, for most business apps, they're going to be just as fast as C++. But when it comes to these super high performance things, then they're not going to cut it.
See a lot of degradation from not well-designed templates and getting into trouble with.
I wouldn't say that the picture there is perfect. In fact, someone was talking to me earlier about some issues. Like remember I talked about how you have to rely on the inliner? That's one example of a dependency on the compiler being good enough. And there's other examples of that as well.
I've had to force the compiler to inline in some cases.
That's right.
It wouldn't do it by default.
Right. So there are, and that's actually one of the motivations for, like in a future version of this, having explicit splicing, because the splicing is basically a way to force inlining. And if you had that built into the language, then the library writer can take a little more control over the generated code.
Questions? Thanks again. And,
Thank you.